All right, so check this out. We're on chapter 7, page 184, 7.2. We're going to talk about gases. And I was having a conversation with one of the other parents inside of your chemistry course, and he was telling me about where the mole actually comes from. And it has a lot to do with gases. And I wouldn't even mind letting him chime in because I got the story, but I don't think I'd do justice, like trying to explain that to you. But essentially, what they did was they filled up these, you can fill up a balloon or fill up some volume. And you can calculate out, if I had 1 mole exactly of some gas, okay? And we have to add the caveat of it being at STP, that's what we call it. STP means standard temperature, standard pressure, okay? And I'll tell you the reason why. And you won't actually learn about, really the heavy part of this until we get to like chapter 10, when we talk about the chemistry of gases and states of matter and that kind of stuff. But I can tell you this, that if I have some gas here, okay, and it's at one particular temperature, you know what a pressure pot is?
Yeah.
Yeah, all right. How do we make the pressure get really high inside of that, inside of that pot, the pressure pot?
Just add more like hot air.
We don't actually add anything to it. It has a bunch of air particles that are trapped in there, right? And they're bouncing all over the place. And then we increase the temperature. And then what happens to the particles inside there when the temperature goes up? Do you know? You can take a guess.
I don't know.
Or I don't know is a perfectly good answer. You don't know?
Don't they bounce around more?
They bounce around more. Exactly. They bounce around more because they're moving faster. And so when they move faster, they're like bouncing off the walls and hitting the walls more often. That increases the pressure. So if we didn't have a pressure pot, or if that were happening in a balloon, what would happen to the balloon is it would expand. It would grow, and that's kind of how the principle of how hot air balloons work. So if we wanted to say, hey, if we're considering a gas, and we put it at the standard temperature and pressure, and the standard temperature and pressure is when the temperature is at 0 degrees Celsius. And we also say pressure is 1 atm. Or, what was it? It was it was 101 kilopascals, 101 kPa. Do you not know what that is?
Royal Farms.
Huh? Oh yeah, it's at Royal Farms. It's where you get the money out of. Okay, ATM stands for atmospheres. And when you go up in an airplane, what happens to your ears?
They pop.
They pop because the pressure is not as great. When you go down deep into the ocean, what happens to your ears? They get pushed in because the pressure is greater. But right exactly at sea level, which to be honest with you, Edgewood High School is just basically at sea level, right? That is what 1 atmosphere of pressure feels like. And then if you go up to like Mount Everest, you might experience something like 0.7 atmospheres of pressure. So it's a way of measuring how much pressure is being done. And so they're saying, hey, if we consider this experiment being done at 0 degrees Celsius and 1 atmosphere of pressure, then you have this new relation, because what they found, this crazy thing that they found is all of these gases pretty much, these what we call ideal gases, pretty much all have the same amount of volume. They take up the same amount of space. And that answer, and this is a conversion factor you guys might want to learn, is that at STP, 1 mole of gas is equal to 22.4 liters. Got it? So that one pretty much always works. 22.4 liters of gas. If I had 1 mole of gas and I kept it at 0 degrees Celsius, it would take up 22.4 liters. Now I can't say that if it were at 100 degrees Celsius, it would probably take up more volume, or if I, had it at a higher pressure, it would take up more volume. But if I'm talking about the standard temperature, standard pressure, then the amount of space it would take up is exactly 22.4 liters. Okay? And we can use this fact in our math. This is just another conversion factor that we can use. So let's try this example. Ready? If we had 0.60 moles of SO2, how many liters does that take up? And this can apply to any gas. So if I told you we have 0.60 moles of carbon dioxide, if we have 0.60 moles of helium gas, or oxygen or nitrogen gas, or any kind of gas, it would come up with the same answer because it would take up the same amount of volume, that 22.4, so long as we're talking specifically at STP, which these problems are going to assume that you mean at STP. Am I making sense here?
Yeah.
All right, cool. So we start off with 0.60 moles, and we have a conversion factor. I'm going to give you the hint is 1 mole is equal to 22.4 liters in terms of a gas at STP. So which goes on top, the moles or the liters? Which one goes on the bottom?
The moles.
The moles. So it's 1 mole over here and 22.4 liters. So what is units go like this, and we got 0.6 times 22.4, and what's the answer? Oh, by the way, this is 7.8 or 7-8.
13.44.
13.44, is that what I got? Yep, I got 13. I got a question. You said it's 13.44. If you were to write that on your homework, on your test or whatever, I might mark you wrong. Why?
Sig figs.
Sig figs. So what's the correct answer then?
13.4.
No.
Oh. Just 13.
Why?
Isn't this 2 sig figs?
Yep. This is only 2 sig figs. So your answer can only have 2 sig figs, so the answer is 13. Cool? Now, I'm not your teacher. I have no idea whether your teacher will burn you on that kind of stuff, although I would if I were your teacher. So make sure, because, and I'll be honest with you. I wrote a report, and I turned it into my boss, and I was like, okay, here's the numbers I got. And he looked at it. He took one look at it, and in 5 minutes, he gave it back to me. He says, okay, I know that you wrote a 56-page report or whatever, but did you consider any sig figs? And I was like, oh, yeah, I didn't consider that from back when I took chemistry like 8 years ago or whatever. So, like, this is actually stuff that you would use in the real world because you want to make sure that you're reporting accurate numbers. So, anyway, yeah. So believe it or not, all the stuff that we're teaching you now actually can apply to your life. I know, it's crazy. All right, let's try this one. Okay, this one was a little weird, but I'll do my best to get through it. We have the density of some gas, and this gas is made up of carbon and oxygen. And the reason why I put the little dollars or number signs, are those hashtags? No, these aren't hashtags.
I think the proper term is a pound sign.
Well, I mean, yeah, the number sign, or yeah, whatever. The reason why I put these little symbols right here is because I don't know if this is carbon monoxide or carbon dioxide. It just says some combination of of C's and O's, of carbon and oxygen, is has a density of 1.964 grams per liter. And they're saying it's at STP. And what they want us to find is what is the, what is the molar mass of the compound? So grams per mole. Got it? And this is example 7-9. Okay. So, how did I do this? Forgot. Okay, here we go. Oh, okay. So I'm going to start off with 1.964 grams per liter. And then what I want is, I want in the end grams per mole. But I know that, I know a conversion, so I don't want liters in there at all. So what I'm going to do is I'm going to multiply this where I have liters on top and moles on the bottom. And I just told you that this is a gas that's at STP, so I know that it's 22.4 liters for every 1 mole of that gas. Does that make sense? And then what I'm going to do is this liters will cancel out with this liters, and I get the units that I'm looking for is grams per mole. So use your calculator. What is 1.964 times 22.4? What do you get?
43.9.
43.9. Grams per mole. Okay, let's see. Oh, you forgot the 4. 1.964 times 22.4.
Oh, shoot.
43.99.
Yeah.
Yeah. But it's maybe okay. Now I'll be honest with you. I don't remember this, and maybe somebody else can chime in. But I'm thinking that this is just 3 sig figs, the 22.4. So I'm going to round it off to 3 significant figures. So 43.9 is going to be my answer. And my numbers might end up being a little bit different from how the book does it. So this is the answer I would put over here. So that's how many grams per mole there are. Now, here's a good question. And this isn't a part of the example problem. This is just I'm curious to know. Is what is this? Is this carbon monoxide? Is this carbon dioxide? I know that the molar mass is this. What is the molar mass of just carbon?
12.
12. And what is the molar mass of oxygen?
16.
16. Okay. So check this out. If this were just straight ahead carbon monoxide, that would be 1 carbon and 1 oxygen. Then I would add these up, and this should have that same molar mass, right? 2 plus 6, that's 8. 2 plus 2, that's 28 if I add those up. Do you think that this unknown compound of carbon and oxygen is carbon monoxide?
No.
No, it can't be, because it doesn't have the correct molar mass.
It's carbon dioxide?
Oh, okay, so another famous gas that you've heard of is carbon dioxide. So if I put a 2 there, that means we would need to multiply this by 2 and make that 32. Okay? This would be 4, this would be 4, 44, 44. Hey, wait a second. I think that we're dealing with carbon dioxide here. Cool? So this is a kind of the way that we can play detective and investigate how this thing is put together. Does that make sense? How's this stuff? Is it like cool, or is it boring? Is it what?
It's cool.
Okay. All right.